mean, I thought it was going live. You're live. Yes, you're live. Okay. 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 Okay, good. Right, let me start now. So thank you, everybody, to come back again to the SPICE and SPIN+X seminar series that I lead here in the SPICE Spin Phenomenon Interdisciplinary Center with the collaboration of Libor Schmekiel, Angela Bittmann, and Karen Overschild now in Duisburg, that we organize in cooperation with the SPIN+X Collaborative Research Center that is led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe here in Mainz. So as you're aware, this is a Zoom webinar, meaning that most of the participants will see the speakers on the web and the panelists. If you have any questions, please write them on the chat or the Q&A during the talk, or after the talk. Just raise your hands or write it in the chat, and I'll manage the Q&A. As everybody knows, it's the same time as always at 3 p.m. in German time and European Central Time. And please keep in mind that we will begin next January again, at the end of January, toward the end of January, with starting with Matthias Chloe already in there. It's my pleasure to finally have Kirill Belashchenko here. Kirill, besides very well known in our field, he's a professor at the University of Nebraska, Lincoln, Nebraska, and has been working on spintronics and computational magnetism and spintronics quite a long time. Very well in our field. We are together the same cultural scholars as well. I got it in 2008. I think I was a year or two earlier. So because I have more gray hair than he does, as you can probably tell. But overall, also he has as well a sister seminar series that is actually very, very well known as well. That started also in COVID, and I consulted with him. Sorry, but during this period. So with that, I would like to please ask Kirill to go ahead and share your screen and start your talk whenever you're ready.
Yes, thank you very much, Jairo. Give me 1 second.
Perfect. Yeah, we see you well.
Okay.
Perfect.
Yeah, thank you, Jairo, for the introduction and for giving me the opportunity to present my work in this excellent seminar series. So my talk will be about first principles calculations of spin transport and spin orbit torque in metallic heterostructures. Let me try to turn on the pointer. Yeah. So this work was done in collaboration with a number of people who are shown here. So Giovanni and Wuzhang are my students at UNL. Wuzhang has graduated already. Alexei is a colleague here. Paul and Mark are colleagues at NIST. Vivek Amin at the University of Indiana, and Mark van Schildgaard at National Renewable Energy Lab. Here are the references to the work that is relevant to this talk. They will show up later. So this is the introduction, the outline. I'll start with the introduction and some earlier results for spin orbit torque and bilayers, which will serve as the basis for further studies from these 3 papers that one was published recently and 2 are preprints. So the first one was on the transverse spin transport in a single platinum layer, and then spin orbit torque in trilayers, ferro, normal, ferro trilayers, and the last one, the exchange-driven spin Hall effect and anisotropic ferromagnets. So by way of introduction, let me remind the prototypical devices that were proposed and have been central to the development of spintronics and spin orbitronics. So it all started with the giant magnetoresistance back in 1988. which, as will be important in the following, can be both current perpendicular to the plane or current in the plane geometry. Then, quite shortly afterwards, the first, I think, device based on spin-orbit coupling in spintronics was proposed as the dot-to-dot spin transistor, where gate control of the spins in the channel is mediated by spin-orbit coupling. The other important concept is the spin transfer torque from a few years later, where we have a trilayer, two ferromagnets separated by a non-magnet, and when we drive the current through the system, we can generate a torque on the free layer, which can be switched and excited and manipulated. And this device does not need spin-orbit coupling. And the next iteration was the spin-orbit torque, which will be the main focus of this torque, where we get rid of one of the ferromagnetic layers. Instead, we use a heavy metal, and we exert a torque mediated by spin-orbit coupling and effects like the spin Hall and Rashba-Edelstein, as I will mention in the following. So again, this is the main focus. A bilayer, normal metal, and a ferromagnet. And then due to charge-to-spin conversion, in the bulk or at the interface, we can exert a torque on the magnetization. And among other things, this allows us to make the device into a three-terminal structure, which separates read and write currents. The write current goes here, the read current goes there through the magnetic tunnel junction there, and that helps endurance of the device, among other things. And it can be used for multiple applications like MRAM, high-frequency nanooscillators, and all sorts of tricks with driving magnetic structures and domain walls, fermions, and so forth. So the basic mechanisms of spin-orbit torque that were understood pretty much immediately when the experiments appeared is the spin Hall current coming from the heavy metal and then absorbed by the ferromagnet, which generates a so-called damping-like torque, which has this form. And this picture shows the direction of the torque as a function of the magnetization on the sphere, where the electric field is applied in the x direction and the z direction is the normal to the film. And the Rashba-Edelstein effect, which comes from the spin accumulation that appears at the interface due to the inversion symmetry breaking, there may be spin momentum locking. So here this shows that situation for a simple case of a Rashba split band. And when we apply the electric field, so the Fermi circle shifts and then results in a spin accumulation, which exerts a torque, which acts exactly like a magnetic field applied in the y direction. So it looks like this, and it winds around the sphere around the y-axis. So this is a precession-like torque. However, in addition to those simple mechanisms that have been understood for a long time, there are, in fact, a number of unconventional sources that cannot be described in so simple terms. And there's quite a plethora of those that have been advanced in the last few years. Spin Hall effect in ferromagnets, interface-generated spin currents, orbital currents. This is not a complete list. These are just some of the most prominent examples. And in addition to this, typical heterostructures used to study spin-orbit torque are very strongly disordered. They're produced by sputtering. And there are a few length scales that are of the same order, such as the thickness of the film, the mean free path, what looks like the spin diffusion length. They're all of the same order. So the assumptions that go into the simple models don't always work. So in order to describe these complicated mechanisms, we use a technique which includes disorder explicitly in a supercell geometry. So this technique is called the non-equilibrium Green's function method. So the idea is that we have an active region, which can be quite a large supercell, which is embedded between the semi-infinite leads, and then we use the Green's function technique to calculate the local observables inside the active region. We can calculate quantities like spin accumulation and spin torque using the torque operator here. And the advantage of this method is that we can take reasonably large supercells and we can introduce disorder explicitly in this active supercell, and the disorder can be Anderson disorder for model calculations, or substitutional disorder, or whatever disorder we think is important. And then we can simply average over disorder configuration. And this amounts to a computational experiment that takes all mechanisms on the same footing. It does not involve a diagrammatic expansion, in contrast to the Kubo linear response technique, where you need to decide, okay, which diagrams you're going to include. Do they include everything or not? There is no concern like this. So in principle, this can be done in a numerically exact way. And the calculation has been implemented in this Kirill package, and there's a reference here. It has a lot of other stuff there, but it can also do spin orbit torque. So just an example of a typical computational cell. So if we have a bilayer, so this may represent the heavy metal and the ferromagnet. So we just arrange a supercell like this. So the end regions can be turned into leads, and then we introduce disorder in the embedded region. The system is periodic in one direction and has a free surface in the other. It has to be large enough, so we actually describe diffusive current. So it needs to be longer in the transport direction than the mean free path, which is not that hard to achieve for typical disorder strengths. And then we just average the observables in the over the disordered embedded region. So here's an example of the calculation results for spin orbit torque in the cobalt platinum bilayer with 6 monolayers of each. It has been separated into an even part and odd in the magnetization. So each arrow here corresponds to the data point from the calculation, which is already averaged over disorder. So we see here the even component looks like damping like torque, and we can extract the magnitude of that torque. And the odd component for weaker disorder, it looks like feel like torque, but for stronger disorder, it looks more complicated. It actually includes higher harmonics, which can all be extracted. And we can find in particular that the damping like torque depends weakly on disorder, which is consistent with the intrinsic mechanism. On the other hand, the feel like torque declines with increasing disorder, which is consistent with the Rashba-Edelstein or inverse spin galvanic mechanism. And then we can vary different parameters and see how the torque responds to those. So one of those parameters is the thickness of the heavy metal layer. So here it's platinum. So we know the prediction of the spin diffusion model. So in particular, this is a picture from this work. We know that the spin Hall mechanism in the spin diffusion model leads to the dominant damping like torque, which starts from 0 and then saturates on the length scale of the spin diffusion length. And the Rashba-Edelstein effect generates predominantly feel like torque, which does not depend much on thickness. And we can compare that with the results of the calculations. So here we vary the thickness of either platinum or gold And we calculate the torque, and we try to fit this to the spin diffusion model. And in this case, we find that we cannot fit it directly to the spin diffusion model, but we can fit it to a spin diffusion model with an offset. So the offset, which is the limiting value at a small thickness, can be interpreted as the interfacial contribution to the spin orbit torque, and we see that it's comparable to the bulk contribution, presumably due to the spin Hall effect. And the other feature we can extract from here is the length scale at which the torque saturates with increasing thickness. So we can call it the spin diffusion length, and we find that it is quite insensitive to disorder, and it's on the order of 2 nanometers in platinum, which is somewhat similar to experimental results in similar kind of measurements. And we'll come back to it later, and we'll see that we get a similar value in a different way. So now I'm turning to the part on the transverse spin transport in a platinum layer. So this is a recent work done in collaboration with Paul Haney and Mark Stiles at NIST, and Alexei Kovalev here at Nebraska, and Mark van Schilgaard at NREL. So the motivation for this work is that while the spin diffusion model is widely used for spin transport and spin orbit torque in bilayers, as I mentioned before, it's not clear whether this model should be expected to be applicable to intrinsic spin currents, because the spin diffusion model operates with the spin currents that are driven by the non-equilibrium distribution functions, and intrinsic spin currents are quite different. Typical spin sources, spin Hall sources like platinum, are known to be dominated by intrinsic spin current generation. In this paper recently, the spin current in a platinum film was studied using a method that is similar to an EGF. It's based on wave functions, but it's fundamentally similar. And they analyzed the results by fitting them to the spin diffusion model, and they found reasonable agreement. Now, I'll show that if we look simultaneously at the spin current and spin accumulation in a diffusive platinum film, as a function of disorder, we see that we cannot reconcile the results with the spin diffusion model, and then this model actually breaks down. So just a reminder about the essential features of the spin diffusion model. So the geometry is very simple. There is a film with free surfaces, electric field applied in the plane. The spin Hall effect generates the spin current flowing out of plane, polarized in the y direction, and then there's an accompanying spin accumulation oriented in the y direction. The spin current has a source term coming from the spin Hall effect and the so-called backflow term, which comes from the Einstein relation, and it is related to the gradient of the spin accumulation. The other equation is the spin continuity equation, along with the local relaxation time, which depends on the non-equilibrium spin density, which in turn is related to the spin accumulation. So we can combine these two relations, and we get the spin diffusion equation. We need to combine it with the boundary conditions at the surface of the film. The boundary condition may include a spin loss conductance times the spin accumulation, plus possibly a term driven directly by electric field near the surface. If we use this boundary condition along with the spin diffusion equation, we can find the spatial profiles of the spin accumulation and the spin current. And the important thing for the following is that they're related to each other. one can define an effective spin-Hall angle that appears both in the spin accumulation and the spin current. It's generally different from the true spin-Hall angle, characterizing the bulk spin current in a heavy metal. But these two parameters, it's the same parameter in both these quantities, and this can be checked in a calculation, whether they're the same or not. So here's the result of the simulation for a 100 monolayer platinum film. So this is the disordered supercell calculation, and the picture on the left shows the spatial profile of the spin current, which we recover from the spin orbital torques, which is the expectation value of the torque from the spin orbit coupling operator, which is equal to the divergence of the spin current. That's the continuity spin continuity equation, so we can recover the spin current at any position in the film. So the x-axis shows the layer, the position across the thickness of the film, and this shows the local value of the spin current. So the three curves correspond to three different values of disorder. So one thing we see is that the disorder dependence is much weaker than the dependence of the resistivity on disorder. This is consistent with the intrinsic mechanism, and the values are also quite similar to the spin-Hall conductivity of platinum, which is known from linear response calculations. We can also look at the energy dependence of the spin-Hall conductivity extracted from this kind of calculation. So here we just put the Fermi energy at different positions, and we get the curve that is quite independent of disorder and very similar to the results of linear response calculations. So we see that the intrinsic spin current is captured by the NEGF method. And then we can look at the spin accumulation. And from the spin accumulation, we extract the spin diffusion length, characterizing the rate of decay of the spin accumulation next to the surface of the film. So this column in the table shows the resulting value, which is almost independent of disorder. It's about 1.5 nanometers. And there are a few things of note about this length. So first of all, this length is similar to the length we found from the thickness dependence of the damping like torque that I showed earlier. There we got about 2 nanometers. Here it's 1.5, but it's quite close. So the other feature is that, as I said, it's insensitive to disorder. So this is not typical for the Elliott-Yaffe mechanism, in which the product with the resistivity is expected to be approximately constant. And the other feature is that this, what we call the transfer spin diffusion length, which we obtained from this calculation, is considerably smaller than what you would call the true spin diffusion length, which you can determine from the analysis of the longitudinal spin current. So we can do a separate calculation where we simply calculate the spin resolved, spin conserving, and spin flip conductances for a bulk platinum region of varying length, and we can extract the spin diffusion length from there by just matching to the spin diffusion model. And there we find values that, depending on disorder, may be a few times larger than the apparent transfer spin diffusion length. And the longitudinal one does depend on disorder, as expected, and the transverse does not. So this tells us that this length scale, which in fact is comparable or even shorter than the mean free path, this length must have a different origin. It's not of a diffusive origin. There is no diffusion on the length scale of the mean free path. It is related to the length scale at which something happens to the intrinsic spin current next to the interface. Unfortunately, we don't have a theory better than the spin diffusion model, so we can't tell exactly what happens, but we see that there's a different length scale that's different from the spin diffusion length. So let me also mention that experimentally, the situation with the spin diffusion length in platinum is not entirely clear. There is a measurement based on the MOC measurement of the spin accumulation in the platinum film that gave the spin diffusion length of about 11 nanometers. But on the other hand, the thickness dependence of the damping like spin orbit torque always gives, or nearly always gives, the length scale of about 1.5 nanometers. So there's a discrepancy between two kinds of experiments, and I don't have an explanation for that. So now we can finally compare the effective spin Hall angles that we can extract from the spin accumulation by fitting to this formula, and from the spin current by fitting to this formula. So as I mentioned earlier, from the spin diffusion model, we expect these angles to be the same, but we find that they are actually quite different. And even their disordered dependence is different. One decreases, one increases. So that tells us that the backflow relation is not satisfied and the transport is not diffusive, which again, perhaps is not too surprising because the relevant length scale is not long compared to the mean free path. So we have a different length scale, which the origin of which we at present do not quite understand. So let me also mention one aspect that is related to the recent topic of interest, which is the orbital torques resulting from the orbital currents. So there's been a large number of papers recently on this topic, in particular the theory in this paper and a few others. And one of the observations that was made recently is that it appears that orbital currents propagate over longer distances than spin currents. And some experiments give length scales on the order of many tens of nanometers, 50 nanometers in titanium, 70 nanometers in tungsten, which are surprising because the relaxation of orbital momentum does not involve spin-orbit coupling, so you would expect that it should relax on the length scale of the mean free path along with the momentum. So if the mean free path is a few nanometers, you would not expect the orbital relaxation length of tens of nanometers. So what we can say, though, is that if orbital relaxation length is long and the phenomenology of orbital diffusion is physically meaningful, then there should be an orbital accumulation accompanying the orbital currents. And we can look at the orbital accumulation in our system. So here we do this for the platinum film that I was talking about. And we can do this both in the presence and in the absence of spin-orbit coupling. So these two results are shown here. The yellow curve is without spin orbit, and the blue is with spin orbit coupling. So we see, first of all, that in the absence of spin orbit coupling, there is no orbital accumulation in the bulk. It's a purely surface effect within a few monolayers from the surface. And we only get a weak diffusive tail into the bulk if spin orbit coupling is included. And the length scale there is similar to the transverse spin diffusion length that we found earlier. So this tells us that this diffusive orbital accumulation is induced by the spin accumulation. So there is no separate long scale here in these calculations. So it is possible that the observed long orbital relaxation lengths in light metals could in fact be related to spin diffusion lengths and different mechanisms. So to conclude this part, we found that the intrinsic spin current in platinum is captured by the energy of calculation. We found, however, that the spin diffusion equations are not satisfied. The apparent transverse spin diffusion length that we can find from the spin accumulation is much shorter than the longitudinal spin diffusion length and close to the mean free path. and also nearly independent of disorder. And the orbital accumulation does not penetrate deep into the bulk, except due to spin-orbit coupling being induced by the spin accumulation. So now I turn to the second topic, which is the spin-orbit torque in ferromagnet, non-magnet, ferromagnet trilayers due to indirect spin current generation. So I will explain shortly what it means. So the motivation to study trilayers comes on the applied side from the interest in enabling field-free perpendicular switching. So conventional damping-like spin-orbit torque can only switch the magnetization oriented in the y direction in the plane in the absence of the external field. To switch the out-of-plane magnetization, one needs to apply an in-plane magnetic field, which is undesirable for applications. So there have been a lot of research on breaking the symmetry in a way that would allow out-of-plane spin torques, and that includes growing films with a structural asymmetry, or using single crystal sources, or ferromagnetic trilayers, which will be the focus of this topic. And in fact, field-free switching of a perpendicular free layer was observed in a trilayer in this paper. So you see there's a current pulse here, and there's a switching between up and down in the structure where we have a fixed ferromagnetic layer, which breaks the symmetry of the system, and the switching of the perpendicularly magnetized ferromagnet. And one of the leading explanations for this effect is that the interfaces can emit spin currents with both in-plane and out-of-plane spin directions, as it was explained in this review and first proposed in this paper. One can imagine the interface between this fixed layer and the normal metal emitting spin currents that get absorbed by the free layer, resulting in out-of-plane spin torques. And here's another measurement in this paper in 2017, where they measured the magnitudes of these so-called spin-rotated torques, which have the polarization that is given by M cross Y instead of just Y. And they found substantial torques with the spin-rotated polarization. And what is important is that they found both damping-like and field-like components. And the field-like component was even larger than the damping-like. So these are both spin-rotated components. And the origin of the field-like component was quite unclear. So the spin diffusion model does not explain that. So to study that, we again use the NFGF method in combination with circuit theory and semi-classical simulations and some symmetry analysis. So this was done in collaboration with Vivek Amin at Indiana and Alexei Kovalev here at Nebraska. So first, we can notice that in collinear trilayers with parallel or anti-parallel ferromagnetic leads, we get effects in the torquens that are similar to the current in plane GMR effects. So the damping-like torque is much larger in the parallel configuration than in the anti-parallel configuration. And the magnitude of this effect decreases with the increasing thickness of the spacer and with increasing disorder. So it qualitatively behaves similar to the CIP GMR. So we may expect mean three-path effects beyond spin diffusion model in the system. So let's now look in more in a more general way on the torques in the trilayers, so we can describe them by a combination of the damping-like and field-like torques plus higher orders, which I will not have much to say about. They're usually small, So the damping-like and field-like torques now have the vectors giving the polarization of the damping-like and field-like torques. We can call them the special fields that may depend on the magnetization of the bottom layer. And the dependence can be quite complicated. So here are some of the terms that are allowed by symmetry, and we can relate them to the known mechanisms. I'm not going to repeat them, but one of these terms appearing here is equivalent to the spin-rotated field-like torque in the measurement that I showed you, but it's a non-local field-like torque with the origin that has been unclear so far. So to understand this term, we can discuss the direct and indirect non-local mechanisms of the spin current generation in the trilayers. So here's what it means. So in the direct non-local mechanism, which I alluded to before, and this is more or less well known now, that the ferromagnet, the bottom ferromagnet or its interface with the non-magnet can generate spin currents, which then get absorbed by the other ferromagnet, and this generates damping-like torque. Now, in the indirect non-local mechanism, what happens is the following. So let's assume that the thickness of the non-magnet is not large compared to the mean free path. That means that the spin current flowing in the top layer, which is polarized according to its magnetization and flowing in the plane, this current, so to say, leaks across the normal metal, right? As the electron enters the non-magnet, before it gets scattered, it still remembers that it came from the ferromagnet. So there's a tail of that spin current extending to the interface with the other ferromagnet, and there, due to spin-orbit coupling, it can get converted through scattering mechanisms that are now well understood into the out-of-plane spin current with a different spin polarization. And the polarization of this current depends on the magnetization of the top layer. So then this current can get absorbed by the top layer and generate a torque, but because it carries an extra dependence on its magnetization, what would have been a damping-like torque is now field-like. So this is the essence of the indirect mechanism, and one can analyze the consequences of that using the circuit theory. I'm not going to bore you with the details. The conclusion is that if we only have the direct or indirect mechanism alone, then the polarization vectors for the damping-like and field-like torques are parallel to each other. So these two torques pass through zero at the same angle when we fix one of the fix the bottom layer, let's say, out of plane, and let the top layer rotate in the plane. This is this angular dependence. But if both mechanisms are present, then the two vectors are not parallel, so we would see a phase shift in these two curves. And now if we do an ab initio calculation for the cobalt-copper-cobalt trilayer, we find that there is a large phase shift. This is exactly the same dependence as on the previous slide. So one of these is damping-like, the other one is field-like. They don't pass through zero at the same point, which is the signature of the presence of both direct and indirect mechanisms. In other words, this gives the spin-rotated field-like torque, which does not come from mechanisms that can be described by the spin diffusion model. And there's additional evidence from semi-classical calculations that Vivek has performed. So this is a fairly standard approach where the Boltzmann equations are solved for trilayer geometry, and it introduces interfacial scattering, impurity scattering, unequilibrium distribution functions. All of that is solved. And then in the end, you get similar dependences of the field-like and damping-like torques, and there is again a phase shift, and that phase shift declines with increasing thickness of the non-magnet, as expected from the mechanism that should only occur when the thickness is comparable to the mean free path. So to conclude this part, there are new types of spin-orbit torque in ferromagnetic trilayers with a thin non-magnetic layer, the thickness on the order of the mean free path, reminiscent of the CIP-GMR effect, which involves the indirect spin current generation at the interfaces, which leads to the spin-rotated field-like torques of the type observed before experimentally. So now I'm moving to the last topic of this talk, which is the exchange-driven spin Hall effect in anisotropic ferromagnets. So, as a motivation for this work, let's recall the recent realization that in antiferromagnets with exchange split bands, which are now called altermagnets, there are a variety of new effects possible in transport thanks to that exchange splitting. And in particular, even without spin-orbit coupling, you can get a transverse spin current in a collinear altermagnet. This was shown in this paper. This is called the spin splitting current. And the idea is very simple. So if we have exchange split Fermi surfaces between spin up and spin down electrons, so the Fermi surfaces are different, so you can get transverse currents that don't compensate each other, and you can get a net spin current flowing in the transverse direction. And the effect is expected to be quite large. And one could use this effect in a trilayer structure using an altermagnet as a source of the spin current, and it could potentially be also used for field-free switching of perpendicular magnetization. So the question I will address is whether this is a similar effect is also possible in ferromagnets without spin-orbit coupling. We discussed before how one can have switching due to spin-orbit torques generated by the bottom ferromagnetic layer, but now can we do that without spin-orbit coupling, and could we potentially get a larger effect there? So one can imagine a ferromagnet. So obviously in a ferromagnet, the two Fermi surfaces are different for the spin up and spin down electrons. This is always the case for ferromagnets. But then let's imagine that the ferromagnet is crystallographically anisotropic, so perhaps tetragonal or hexagonal. So then the response of the current to the electric field involves a conductivity tensor, which is not just a scalar. So you can have transverse charge and spin currents in this case. So what happens if we turn this ferromagnet into a film? We use it in multi-layer geometry as typical for spin torque switching experiments. So then there can be no transverse charge current because we have open boundary conditions. So there will be a Hall voltage that creates a transverse field that cancels the transverse current, but we can simply write the equations for the different components of the current and impose the boundary condition and find what one would call the spin Hall angle, which is the ratio of the transverse spin current to the longitudinal charge current. So if we do that calculation, which is very straightforward, one gets this answer for the spin Hall angle. There's a geometric factor that depends on the angle that the crystallographic axes make with the normal to the film. So here we assume one of the principal axes is in the plane, and then two others make an angle theta, and we drive the current in the plane spanned by those two axes. So this is the geometric factor. The maximum value here is 1 for 45 degrees. And then here is the difference in the transport spin polarization. This beta is the standard transport spin polarization for the conductivity tensor along one of the principal axes of the tensor. So here, it's the difference of the transport spin polarizations along the z direction and along the x direction. So the maximum spin polarization is 1, so the maximum value of the spin Hall angle is 1. And it could be positive or negative. And this spin Hall angle describes the source of pure transverse spin current due to anisotropic to the anisotropy of the ferromagnet, which is not accompanied by any charge current. That's the assumption. So the transverse charge current is assumed to be 0. So this is not just a transverse spin polarized charge current. Of course, the spin current will generate some spin accumulation. So the spin current profile in the device must be determined from the spin diffusion theory for the multilayer, where this spin Hall effect will serve as a source inside the ferromagnet. If we look at the anisotropy of the transport spin polarization more closely, of course, we don't have spin-orbit coupling. We assume it's all exchange driven. So response is purely extrinsic. So we can reasonably use the relaxation time approximation. The conductivity tensor is proportional to the relaxation time. So let's assume it depends only on the spin. So we can take it out of the integral. And then we have two factors here: the anisotropy of the relaxation time and the anisotropy of the electronic structure. So the anisotropy of the electronic structure, this is sometimes called the plasma frequency tensor. This is easily calculated. The spin dependence of the relaxation time is usually not known, but if we express the difference of the anisotropy of the transport spin polarization through the anisotropy of the relaxation time and the electronic structure, we see that the decisive factor is provided by the anisotropy of the spin polarization of the K tensor that describes the electronic structure, which is easily calculable. So of course the anisotropy, the spin dependence of the relaxation time will affect the spin Hall angle, but the decisive factor is the anisotropy of the K tensor. So we can use this difference P1 minus P2 as a descriptor to search for and to estimate the spin Hall angle in ferromagnets, and it should be a reasonably good descriptor. We took a number of materials from materials project. Those are all ferromagnets or ferrimagnets with tetragonal, hexagonal, or orthorhombic structure, excluding actinides, those that don't have reported magnetic phase, or those that are expected to have a small spin Hall angle. So the resulting pool includes 41 compounds, which will be quite representative. And then one can calculate the anisotropy of the spin polarization and the predicted spin Hall angle based on that, assuming relaxation time is spin independent. And this gives us a range of values, but typical values are about 0.1, 0.2. So 63% of the materials have the spin Hall angle larger than 10%, and about a third have it more than 0.2. So this compares favorably to the best heavy metal sources like platinum or tungsten. Now, a practical aspect that one has to bear in mind is that in order to generate the effect, we need the crystal to be misaligned, right? If it's a tetragonal crystal, the C-axis cannot lie in the plane, cannot be out of plane. It has to make an angle with the film surface. So this requires a suitable substrate, and this table lists a substrate in most cases, as reported by Materials Project, which provides a good lattice match for this misaligned growth. But in the majority of cases, if you just pick a substrate at random, it will allow orientation domains. I will explain in slightly more detail what it means shortly. But orientation domains give different spin Hall responses, and it is possible that when you average over orientation domains, the macroscopic response may vanish. In some cases, like those highlighted here, the symmetry is low enough so that there is a macroscopic response, but this requires a special choice of the substrate. So this is what I mean when I say orientation domains. So imagine that you have a substrate which has a C4V symmetry, and you grow a ferromagnet on top of it. So there would be misaligned direction of the axis by assumption, but then one can generate energetically equivalent configurations by applying the operations of the point group of the substrate and generate different orientation domains of the ferromagnet. And then if we assume in this case that the magnetization of the film is uniform, so we just magnetize it by the magnetic field in the plane, and the anisotropy is not strong enough to do anything about this direction, then it will turn out that in this particular case, even when a particular orientation domain allows the spin Hall effect, the macroscopic effect may average out to 0. This doesn't always happen. So there are examples of substrates with sufficiently low symmetry, and there are symmetry conditions. I just won't explain what they are, but you can find them in the paper. There are examples where the average is finite despite the existence of orientation domains. So maybe there are no orientation domains at all, in the sense that there's only one. On the other hand, there's an opposite case when the magnetic anisotropy is strong, when the magnetization is parallel to the C-axis, to the crystallographic C-axis. In this case, if we magnetize the sample out of plane by an external field, then it turns out that the macroscopic effect, the macroscopic spin Hall effect, never vanishes for any substrate. This comes precisely because the spin is coupled to the crystallographic direction, and it serves as an effective spin momentum locking, if you want. So to conclude this part, crystalline ferromagnet with tilted axis generates pure transverse spin current without spin orbit coupling, with typically large spin Hall angles. Orientation domains are a practical concern, but some substrates allow macroscopic spin Hall effect, even for a uniformly magnetized film. For strong magnetocrystalline anisotropy, you always get macroscopic response. And then as a result, one can implement a spin orbit torque-like 3-terminal device configuration, but without spin orbit coupling. So it will not be a spin orbit torque anymore. It will be a spin torque, but of a similar symmetry. So this is the graphical summary of the talk. Thank you for your attention. And I'll hand it over to Jairo.
Okay, thank you very much. That was a great overview of many aspects of spin orbit torques and trilayers and devices. So now we are open for questions. If anybody has questions, please raise your hand. Okay, I guess Matthias let me promote you there to there. So he's coming. As he's coming, he will be joining us in a couple of seconds. Let me see. Yeah, Matthias, go ahead and unmute yourself to ask your question. Yeah.
No, thank you very much. Very intriguing. I was very intrigued by this part of the kind of like trilayer system, the ferromagnet with the normal metal in between. You detailed like the thickness dependency on this normal metal interlayer. Is there anything you can say about the thickness dependency of these two different ferromagnetic layers?
So we would expect that if the thickness is large compared to dephasing length, then it's saturated.
Okay.
Right. So if the thickness is too small, so that the spin currents are not fully absorbed, then you could get effects that look like a large imaginary part of the spin mixing conductance.
Okay.
Right? But usually those spin dephasing lengths are fairly short.
They're like monolayers, right? Of the ferromagnet.
A few monolayers, yeah. But I mean, it depends on the material. Something like nickel, let's say, could have a longer spin dephasing length. Right? But that would be the characteristic length in this case.
Okay, thank you.
Yeah, I have a question. I'm intrigued by the orbital component. These results in there. So I mean, it's a bit clear, of course, that without spin-orbit coupling, you still need spin-orbit coupling if you generate even a spin currents or orbital currents, angular momentum currents to transfer it eventually. It is a kind of like a a funnel that you have to go through no matter what. But in here, are you saying that in your calculations, effectively, this orbital spin currents or angular momentum currents, I wouldn't call it spin currents, but orbital angular momentum currents, they are not leading to a strong spin accumulation with the lengths that you expect?
So they are not leading to orbital accumulations. Right. This is orbital accumulation, not spin accumulation.
Right. Angular momentum orbital.
So there is certainly an orbital current in the system. We cannot easily calculate it in the same way that we calculate the spin current because there is no orbital continuity equation, but we can look at the orbital accumulation. So the point I'm trying to make is that physically, I don't see the mechanism for the orbital diffusion to have length scales longer than the mean free path. Right? Because orbital current, speculating a little bit, orbital current is carried by hotspots in k-space. So as soon as you're scattered out of that hotspot, you lose all of the orbital momentum. Right? So there should be no long length scale based on that consideration for the orbital diffusion. Right? The whole concept of orbital diffusion is somewhat questionable. And this is a little piece of information confirming that in this calculation. So if we turn off spin-orbit coupling, then if orbital diffusion phenomenology was relevant and there was a length scale, we would see it in the orbital accumulation, but we don't. The orbital accumulation is only finite within a handful of monolayers from the surface, and then it's just zero, unless spin-orbit coupling is turned on, in which case you get a little tail in the orbital accumulation, and it can be explained through the interaction with the spin accumulation.
And when you mentioned that you expect only the hotspots in the orbital component to be the one responsible for this orbital currents, what do you mean exactly by that? Whereas I can see the connection to the spin, to the gauge fields created by the various curvature in the spin sector. Do you expect something similar to occur in the orbital one?
Well, I'm referring to the usual explanation of the origin of the orbital currents, right? So electric field mixes the filled and empty states, which, despite the fact that normally orbital angular momentum is quenched, despite that, through that coupling of the filled and empty, you could get complex wave functions with which carry orbital current, but that coupling depends on the wave vector, right? So the typical explanation from the calculations is that there are hotspots in k-space. It's not essential that there are hotspots. What is important is that this orbital momentum is a property of a particular k point, right, where there's a particular coupling between the filled and empty states. And then when you scatter from one k point to another one that is far away on the Fermi surface, you get into a state with a completely different orbital momentum, right? And there is no correlation between them.
They will average out.
Yeah, and there is no small parameter in the scattering amplitude that tells you that, let's say, if you start with m equal +2, you should end up with m +2.
In this disorder model, you're still doing the same quench disorder model
Yes.
layer in these calculations, right? Similar to what you did for the spin Hall
It
effect.
is, right. The argument would not be valid if disorder was long-ranged, so that you can only scatter by small wave vectors.
Right.
But typically in the spotted systems, I would expect disorder is essentially atomic length scale. So every scattering event would be across the entire Fermi surface.
Okay. You're pretty homogeneous. Okay. Very interesting. Yeah, there's still a lot of puzzles there to see. For me, it's always a puzzle that you still need to spin coupling. So on the other hand, if experimentally you're seeing large signals that are not easy to explain away with just simply spin Hall effect.
Of course. By no means I'm saying that there are no orbital torques. All I'm saying is that it is about the length scales. But when we analyze experiments with these light metals, in addition to orbital torques, one always needs to bear in mind that there are also self-torques that are possible. Right? You can have a self-torque generated by sources in the ferromagnet.
Yeah, this is the same thing as we found in gallium manganese arsenide and gallium antimonide, those.
Right, but then those torques can also have a thickness dependence on the thickness of the normal metal, because if the ferromagnet emits spin current across the interface, there will only be torque if that current can be absorbed somewhere else.
Yeah, you need a sink.
Right? So you need a sink, and the characteristic length scale for that is the spin diffusion length.
Yeah, correct.
And I'm not surprised at all that titanium would have a spin diffusion length of 70 nanometers or 50 nanometers or whatever it is, right? So that mechanism could give that kind of length scale.
Interesting. Yeah, but the breaking of the symmetry at the interface. So. Okay, excellent. Yeah, that's a good food for thought. Yeah, any more further questions from the? I think we're now down to a few. I guess today not. I think today was kind of like the winding down of. I think that you kind of in the grants in the border with people going vacation most of the time. There's a few more questions. Right. But do feel free to contact Kirill if you have any further questions. If you're actually watching this afterwards, as most of you are actually nowadays, please feel free to contact Kirill. Belashchenko is easy to find him in Nebraska's web department, the physics department. So because he has quite a few things that he's covered today. And with that, I would like to wish all of you a very, very happy Christmas and a very successful and very exciting, full of exciting science and lots of PRLs, lots of grants above all, and everything that comes with it, and staying healthy for the coming year. And we hope to see you guys online and also live, sometimes in SPICE, sometimes here in Mainz, I hope. And thank you once again, Kirill, for coming. Thank you, Matthias, for joining us from the forest back in Kaiserslautern. I tease the guys in Kaiserslautern a lot. Since they don't have as much wine as we have. We have a very large forest. And with the rest of you, have a great time. I'm going to stop here. 1 second. The live.
Thank you very much. Thank you.
And thank you once again.